Good morning, good afternoon, good evening, class. This is Mr. Arosena, and today I'm going to talk about the quantum mechanical model of the atom. Now, yesterday in class, we did a short activity. Well, it's not really short. We did an activity, and we were looking at spectral lines, or the spectrums of various things. So we looked at the spectral lines of fluorescent lights, we looked at the spectral lines of the nitrogen tube, and the spectral lines of Bunsen burner flame, and then we looked at the spectral lines of some of the metal salts that we ended up burning. Okay. So today we'll give a little explanation as to why these spectral lines occur. Okay, so before we do that, though, we're going to talk a little bit about light. So the last time you guys saw light was probably in Science 8, if I remember correctly. And light, if you remember from Science 8, has three distinct properties. It is a wave, and it has these three properties. The first of which is amplitude. Amplitude is just how, well, I should draw the resting position. Amplitude is just how high this crest is or how low this trough is. Okay. Wavelength is how long the wave is, or basically how long it is to go from one point of the wave to the next point of the wave. You can measure wavelength from here to here as well, or from here to here. Basically from one point of the wave to the next point in the next wave. And then the third property it has is frequency. And frequency is just a measure of how often the wave occurs per second. Occurrences per second. Okay. So some waves occur very frequently, other waves do not occur very frequently. Okay. So these are the properties of waves that we learned or talked about in Science 8. Now, moving on from here, one interesting relationship between the frequency and wavelength is that if you were to take the product of the frequency and wavelength of light, this will always equal the speed of light. So the wavelength is usually given by a symbol lambda. So this is wavelength. So wavelength times frequency will always equal the speed of light, which we give the value c. For those of you who have not taken physics, which is I think most of you, the speed of light is equivalent to 3.0 times 10 to the 8 meters per second. And so it's very, very fast, very, very fast. And the speed of light is always constant. It is always this value. Okay, at least in a vacuum. Some substances will cause speed of light to change, but regardless, this relationship is true for light. Always true for light. Okay. Now, because of this, it turns out then that the wavelength and frequency will end up being inversely related to each other. What this inverse relationship means is that if wavelength goes up, so if wavelength goes up, then frequency will go down in order to maintain this relationship. Similarly, if wavelength goes down, then frequency will go up. Again, because this relationship is true for light, where the product of wavelength and frequency is equal to the speed of light. Since the speed of light is always constant, they show this relationship, where if I were to decrease the wavelength of light, then the frequency would go up. If I increase the wavelength of light, the frequency will go down. And it's a neat property of light. It allows us to do some interesting things with it. Okay. So this property arises again because the product of wavelength and frequency is equal to the speed of light. Okay. We'll have to keep this in mind for the future. Now light, again from Science 8, we know that light is an electromagnetic wave. And as such, light has a lot of interesting forms. If you remember from Science 8, the electromagnetic spectrum ranges from radio waves, which are pretty long. I should make note that these numbers are wavelength. wavelengths. So radio waves have wavelengths of about 100 meters or longer, and microwaves are also light waves or electromagnetic waves: infrared light, ultraviolet light, visible light, X-rays, and gamma rays. Now, visible light makes up only a very, very small portion of all electromagnetic waves, but this is the portion that we see. So some things can see other parts of the spectrum, like bees. Bees can see ultraviolet light. Some snakes can see infrared light. But we're limited to the visible light. So whenever we see light, we only see this small spectrum here. We're told our eyes cannot see anything longer than red light, and we can't see anything smaller than violet light. Okay. Now, what does this have to do with what we did yesterday? Well, as you remember, I mentioned earlier, both yesterday and earlier in some of our other lessons, that electrons have the ability to jump to higher energy levels. Okay, so when an atom absorbs energy, so like in the case of yesterday when you were setting the sticks on fire, you were giving the atoms energy. And as such, the electrons in that atom would then jump to a higher energy level. Now, as I mentioned before, electrons don't like to stay at a higher energy level. It makes them unstable, so they want to drop down to a lower energy level. Okay, so the electrons will almost always jump back down to a lower energy level. Now, that lower energy level might be the same energy level that it started with, or it might be a slightly higher energy level than it started with. It all depends on how much energy the electron picked up, and then depending on what series of steps it takes to go back down to a nice stable energy level. Okay. Now, when they drop down in energy level, they have to release an amount of energy. Because remember, when we were talking about the quantized energy states of the atom, so if this were the nucleus, you would have your different shells. And then the electron, if it gained enough energy, if it gained enough quantum energy, it would jump to the next level. And then once it's there, it could drop down to here, or it could drop down to here. And regardless of where it drops down, it's going to release a bunch of energy. Okay. Depending on how far it falls, it'll release more energy. If it falls down only one step, it'll release less energy. But the idea is that when it falls down, it releases energy. Now, this energy is released as a form of electromagnetic radiation. So sometimes we can see it if it gets emitted as visible light. Sometimes we can't see it if it gets emitted as infrared or ultraviolet, or even gamma rays or radio waves. Okay. The idea that is that when the electron falls back to a lower, more stable energy, it releases an energy in the form of electromagnetic radiation. Now, each of those energy levels, because they are quantized into small chunks, or I guess specific chunks, each drop of energy is somewhat unique. Okay, and then depending on the element and the amount of electrons being excited, the electrons tend to fall back down in the same way. So in this way, each element will have a very unique atomic emission spectrum. And you guys will probably, if you observed the copper spectrum and the lithium spectrum from the other day, that showed quite clearly that copper and lithium have very, very different emission spectrums, because copper and lithium are very different elements. They have different amounts of electrons and so on. Okay? So this atomic emission spectrum is just the range of colors produced by the falling electrons. Okay? So as the electrons fall, again, here I'll draw a slightly bigger diagram. Okay. So if an electron gains energy and jumps to here, when it falls down, it's going to release the same amount of energy. Now, however, that electron could choose to fall down to only this level, in which case it'll emit some energy. Now, the neat thing is if it falls to this level, it can actually fall down again and release another EM wave with a third energy. So this one here will release some energy, this fall here will release another amount, and this fall here will release a third amount. So this particular electron could release up to 3 different colors of light. So this would explain, for example, with copper. The copper spectrum had a little bit of blue, a little bit of green, actually mostly green, and a little bit of red. And that could be represented by the electrons falling 3 different times or having multiple paths to get back to its original spot. Okay. To give an example, we'll use hydrogen. So here's hydrogen. The visible spectrum for hydrogen, if we didn't actually have a sample of hydrogen, but if we did, this is the kind of spectrum you would notice. Okay. So this hydrogen has 1, 2, 3, 4, 5 lines, very distinct lines. If you guys observed the fluorescent light, it's very similar, but the fluorescent light has, I think, a little bit of green and yellow in here as well, but still 5 very distinct lines. Now these lines are produced when the electrons jump down from the n equals 2 energy level, or the second energy level. Okay. Oh, and higher also. So basically, the electrons will gain energy, and they tend to gain huge amounts, or depending on how much energy they gain, they'll jump to very high energy levels, and then they'll drop down. So, for example, this drop from a very high energy level down to here will emit one type of light, very high energy light, because it's dropping down quite a few levels. This one here will emit its own light, which will be slightly less energetic than this one. This one will emit light, which is less energetic than this one. This one will emit some light, again, less energetic than the previous one. And then this one will emit the least amount of energy because it's not dropping very far. Okay, so there are 5 possible drops in the case of a hydrogen electron being boosted to a very high energy level. So this would be like, here's an electron. It gets boosted to an infinitely high energy level, and then it just starts dropping according to these. So it's got 1, 2, 3, 4, 5 different drops it can make. Okay. And as such, it'll emit 5 different lights, which we can see here. We have 5 different lights all here, all corresponding to how much energy is being released. Okay. Now this is hydrogen spectrum. Other elements will have different spectrums, again, based on how their electrons gain energy and how their electrons fall back down. Okay. Now, the frequency of the electromagnetic wave is directly proportional to the amount of energy that is lost. So, the more energy that you lose, the higher the frequency of the electromagnetic wave. Okay. In this way, if you drop a particularly large amount of energy levels, you could generate, or your particle could emit an electromagnetic wave that we can't see, either in the ultraviolet light or in the gamma ray section, or so on, or even maybe X-rays or things like that. Okay. And that all depends, again, on just how far the drop in energy is and how much energy the substance or the electron is emitting when it makes that fall. Okay. Now, electrons will only give off energy if they are going from a high energy level state to a low energy state. So if you look on your Aufbau diagram, that'll help you determine whether a particular drop from one orbital to another will emit light. Okay. And remember, there are some cases where the the higher energy level actually is at a lower energy level than the preceding ones. For example, like the 4D is actually slightly lower than a 3P. Yeah, 3P, I believe. So keep that in mind. Also, sorry, 3D is lower than 4P. So keep that in mind that there are some cases where the energy level is slightly lower, so that it may not seem like it should emit energy, but it actually does. Okay, but again, use your Aufbau diagram to help you out when determining that. Alright, so that's kind of a nice little explanation as to what we were seeing yesterday in our lab with the emission spectrums and why atomic emission spectrums exist. Okay. Alright, your assignment for today then is as follows. If you have any questions, come talk to me on Friday. Oh, and yeah, come talk to me on Friday.